Your test on Friday is freakishly long. Time will be an issue. Write this down. There's 50 multiple choice questions. Write it down. 50. And 4 pages of free response. 50 multiple choice, 4 pages of free response.
What is the name of this test? What do you want?
Structure.
Just atomic structure, okay.
4 pages of free response. Okay? Now, the 50 multiple choice questions are bang, bang questions. If you know the stuff. I mean, if you know your stuff, you're going, oh. Ah. If you don't know your stuff, you're screwed. Yeah, might as well just stop. Okay? So they're not hard questions. And I would kind of give yourself 25 minutes for the multiple choice. That gives you how many per question? 30 seconds. That's enough. So time will be an issue, so we're going to have to work on that. And by the way, since there's 50 multiple choice questions, that means that each question will be worth 1 point. So you could miss 10 of them. And if you're perfect on the free response, and still get an A. Okay? That's okay. Okay. I'm going to mention a bunch of terms and words and concepts, and I would write them down and make certain that you have those mastered prior to the test on Friday. So here we go. Electron configuration. I would start with percentages, David. Yeah. Both long and short form, right? How about this? Dot structure. Dot structure is all over this test. I went dot crazy with this thing. Matter of fact, let me piggyback on dot structure, because the dots in the dot structure represent valence electrons. Write that down, valence electrons.
You mean Lewis dot structure?
Lewis dot structure. All right, how about this? Write down isotopes. Isotopes. Write down isoelectronic. Write down ions. Write down number of protons, number of neutrons, number of electrons. You better know how to do that. That's easy stuff, right? Write down light calculations. C equals lambda nu, right? Where lambda is the wavelength, nu is the frequency, c is the speed of light, which is 3 times 10 to the 8th. I'm going to leave these on the board. Okay? How about E equals hv, where h is Planck's constant, 6.63 times 10 to the negative 34th joule seconds. V is frequency. You might also want to know the relationship, that the larger the wavelength, the shorter the frequency. The shorter the frequency, the shorter the energy. Which means that wavelength and frequency are inversely proportional. Frequency and energy are directly proportional. Okay? What? Yes.
I need your help identifying. You said there's 4.
There's 4. You're going to have to figure it out on your own.
Okay.
Okay? There's spectroscopy. Write that down. Emission spectroscopy, absorption spectroscopy. SV spectroscopy. Okay. The old dead people, like Jonathan Dalton, Thomson, Rutherford, Bohr. And your models. All right. How about the periodic table? You need to know everything about the periodic table. You need to know that everything on this side we call metals. Everything on this side we call nonmetals. Except for these guys right here, they're called what? Metalloids. Okay, so metals, nonmetals, metalloids. Matter of fact, this group right here, remember we call them groups, families, and columns. This group right here is called the alkali metals. This group's called the
Alkaline earth metals.
This group right here is called the
Transitional metals.
metals. Okay? Over here we have the noble gases, the halogens, and the
Chalcogens.
Okay?
It's like chocolate. Chalcogen.
Chalcogens. You need to know that the the ones that are in black are solid at room temperature. The ones that are red are gases at room temperature, and the ones that are blue are liquids at room temperature. Okay? Remember, going across, that's called periods and rows. Okay? Like you row your boat. All right. What else? So, like I might say, name 3 things that the alkali metals have in common. What would be one?
One valence electron.
They have one valence electron, which means they have a dot structure of 1.
Boom in water.
They go boom in water. They're highly reactive. Okay? Anything else?
They're all metals.
They're all metals, except hydrogen's not really part of that group, but they're all metals. They all end with S1, right?
Mm-hmm.
They're all solids at room temperature.
They're all solids at room temperature. These are all good things. Okay? Now let's talk about trends. You need to know the trends as well. For example, atomic radius, the size of an atom, gets bigger going this way and down. So why do they get bigger going this way? Matter of fact, the better question is probably worded, why do they get smaller going this way?
Atomic radius?
Yeah, why do they get smaller as they go that way?
Yeah, more protons.
There's more protons, and when there's more protons, they have a larger charge, a positive charge value. Therefore, the Coulombic force of attraction gets stronger. I would write that down. Coulomb's law. Did you write Coulomb's law down? So as we go this way, there's more protons. The more protons, the stronger the Coulombic force of attraction on those outer electrons, and it gets smaller. Why do they get bigger as we go down? There's more energy levels. If there's more energy levels, this value goes up. And if this value goes up, my Coulombic force of attraction goes down.
Down.
And therefore, it gets bigger. Okay? Everything else, for the most part, increases going this way and up. Atomic radius is the only thing that goes this way and down. Everything else, like ionization energy, I'd write down ionization energy, which is the energy needed to remove an electron. That increases going this way and up. Why does it increase going this way? I just said it, people.
Electronegativity.
There's more protons. As I go this way, there's more protons, which means this value goes up, which means my Coulombic force of attraction goes up.